Can you see my screen?
Yes.
Okay, thank you, Xiangyu. And okay, in this part, I will be introducing the graph neural network-based recommendation systems. The existing recommendation methods follow a general supervised learning paradigm. Given the user item interaction matrix, first, we can transfer each interaction into a separate data instance. Second, we feed these interactions into a supervised learning model to perform the prediction, including the representation learning and the interactions modeling. Here, we can use any deep neural network techniques to achieve these two steps. However, such a general paradigm treats each observations as an independent instance and ignores the implicit and explicit relationships among the instance, and we call it the information isolation issue. In fact, there are actually exists a potential relationship among the users and items. For example, there are behavior similarities among the users and items. This adoption of information isolated isomers in such a training paradigm overlooks the relations among the instances, which may result in the suboptimal performance. On the other hand, data in recommender systems can actually be represented as the graph structure data. For the first as can be represented as graph structure data. The first one is the key graph. We call it the user item graph, denoting the interactions between the users and items. The second graph usually exists in the social network size. We call it the user-user social graph, denoting the relationship between users. And the last one is the item graph, denoting the substitutable and complementary items, or the items in external knowledge. Considering the data of recommender systems as graph can provide great opportunities to explore and exploit the relations among users and items, so as to alleviate the information isolation issue. Then the question here is how to model such graph structure data while still achieving promising performance for recommender systems. One of the potential solutions is to consider the data of the recommender system as a graph and then employ the power of graph neural network techniques to explore and exploit the relationships among instances in the graph. So first, what is graph neural networks? Reason is the graph neural network techniques have achieved great promising performance for graph data by learning the meaningful representations. The main idea with them is iteratively aggregating the feature information from the local neighbors using the neural networks. At the same time, no information can be propagated through the graph after the transformation and aggregation. As you can see in this example, the graph neural networks can naturally integrate the node information as well as the topological structure. Given this advantage, graph neural networks provide great opportunities to alleviate the information isolation issue and advance our recommendation methods. Here, I will briefly introduce the formulation of GNNs and see how GNN model work. So let's think of the following. For each node, for example, we have a representation, and the subscript help us at one level of the neural networks and the operation. So at the level yellow of the networks, the representation for node V is the node feature vector. Then we will have the inner layer of the neural network. We will have the representations for given nodes at each layer. And then the representations at the final layer of the neural networks is our final embedding of the node. Now, we need to explain what's happening here. The sigma is the nonlinear activation function, like the red root. And now, what is happening here? What we are doing here is to compute the representations for node V at layer K. Let's go over the neighbors of node V and take the representations of the neighbors from the previous layer K-1. Then we can average these neighbors together. This is the most straightforward aggregation operation. So essentially, what I'm saying here is, this is the node for V, and we check who are the neighbors and layer K. And then we take the message and average them together. And here we have two parameter metrics, W1 and W2. Note that we combine these two messages, this message from the neighbors with the message from itself, from the previous layer. So this is the a straightforward GNN model. There are other variants GNN model, like the graph stage or the GAT. This is the type of aggregation we was introduced before. And now the graph stage use a general aggregation function. And what kind of function we can use? What we did here, what we did before, and we were simply using the mean aggregation function. And we simply take the message from the neighbors and add them up, and then do the normalization by the number of neighbors. And we also can do the pruning approach. For example, we can do the element-wise, the mean or mass pruning. So this would be another option. And then if you like, you can even use a deep neural network like the LSTM to be able to learn how to aggregate the neighbors. The purpose of the using LSTM is to reshuffle the neighbors. Another representative GNN model is GAT, short for the graph attention network. The GAT implicitly assigns the different weight to different nodes in the neighborhood. So here the alpha VU is a nullable attention weight, indicating the importance between node V and its neighbor U. And for more about graph neural network techniques, you can refer to the book, The Deep Learning on Graph by Yao Ma and Professor Jinliang Tang from the Michigan State University. Also, you can download the ebook via this following link or scan the QR code. Also, they also translate this book to Chinese, and you can get it at gd.com. Let's go ahead. Now, we are going to introduce some representative graph neural networks based recommendation methods. Here, I will introduce recommendations with 3 categories. So the first one is purely based on user item interactions, which means we do not have any other side information for users and items. And the other tools are the graph neural network based recommendations with some side information enhanced. This kind of side information can be the social network enhanced. We call it the social recommendations. which can help enhance the user embedding learning. And the items knowledge graph information, which can enhance item embedding learning. Let's first go through the GNN-based collaborative filtering methods. And given the user item interaction matrix with the values 1 and 0, we can easily induce a bipartite graph with the users and item nodes. While there are some difference in some case, we can have other types of interactions, right? We call it the weighted interaction matrix, denoting the rating scored given by users to items. Let's say in the movie recommendations, we can have a 1 to 5 star rating systems. A 1 represents I hate it, 3 is neutral, and 5 as I love it. So in this case, we have bipartite graph with the rating age. And how to model this kind of weighted interaction matrix? One of the most representative methods is GCN, short for the graph convolution matrix competition. So for example, to learn the user representation in this scenario, GCN first aggregate the neighbors information for each weighting value R. Here, this model adopts the weight WR to make differentiation for specific rating value R. Then these methods accumulate all the rating specific representations to finalize the user representation for each user. In a similar way, the item representation can be learned. Another representative model is NGCF, which was proposed in IJCAI'2021. Here in this paper, the authors propose a novel framework, neural graph collaborative filtering to exploit the high order connectivities in user item graph by the embedding propagation. Here, for the node, for the user node, they first compute the aggregation information from its neighbors in this equation, and then the collaborated signals. And then they refine the node embedding based on the aggregate teach information and itself embedding information. And last, we can get the philo node embedding by concatenating the node embedding from different layers, as shown in these equations. Although the NGCF have shows promising performance, some research argues that there exists a unnecessarily complicated design in GNNs for the collaborative filtering. And this model is the LightGCN, which was proposed in IJCAI'2020. They empirically found that the feature transformation and the nonlinear iteration may contribute little for recommendation tasks. Therefore, they propose to simplify the design of the graph convolution network and propose the nice convolution and the nice combination for recommendation. Specifically, LightGCN learns the users and the item embedding only by linearly propagating terms on the user item interaction graph, and then use the weighted sums of embedding learned at all layers as the final embedding to do the prediction. To sum up, they removed the feature transformation and the non-linear iteration in the NGCF model. And despite their success, most existing GNN based recommender systems overlook the existence of interactions caused by unreliable behaviors, such as the random click or byte clicks, and they uniformly treat all the interactions. Here is the general propagation rules in most existing GNN-based recommendation methods. The item embedding here, EIK, is equally propagated or to all relevant users. This may lead to suboptimal representation learning. For example, in this example, with the financial instance, some seller can sell their items with attractive export features, like the headlight or the covers of the items, so as to deliberately mislead the user freeze, which is known as the clickbait issue. And the user too is interested in the electronic products. He purchased one-time items, the handbag, for his mother's birthday present. Worse still, such unreliable feedback may dominate the entire training data set. And it's also very hard to identify. So it may hinder the recommender systems from learning the actual user and item representation based on the user item graph, and may recommender systems were vulnerable to these unreliable interactions. So to verify the non-robustness of such embedding propagation, we conduct a preliminary study to assess the performance of the LightGCN by adding different ratios of random noise. From this figure, we can know that the performance of LightGCN significantly dropped when the interaction between users and items become more noise, which confirms our discussion. And to adjust these drawbacks, we propose the graph change networks for recommendations with principal designs that can capture the adaptive reliability of the interactions, can help us build a more reliable and robust recommender systems. And the existing GNN propagation can be formulated as solving the 9+ themes as smoothly as problem to enforce the embedding smoothness over the user item interactions. It also can be revisited in an edge-wise form. Here, the embedding propagation essentially enforces the user embedding EI and the item embedding EJ to be close if there exist interactions between them. So motivated by the concept of the change filtering and the graph change filtering, we propose the embedding smoothness objective for the user item graph in recommendations. Here, the first preserves the proximity with the initial embedding of the users and items. And the second term, it posts the embedding smoothness over the interactions. And for we now investigate the robustness of different GNN-based recommendation methods under the different ratios of noise age in the user item graph. From this graph, we can see that our proposed methods with the blue color, it consistently outperforms all other baselines, the NGCF or the LightGCN. It means that our methods can effectively resist the random noise in the user item graph for recommendations. Specifically, the performance of the LightGCN significantly dropped when the perturbation rate is larger than 20%. And the performance of NGCF is almost worth those relatively stable against the random propagation. And our GTN model maintains this high performance across different noise ratios, which can demonstrate its superior robustness. And for more information, you can refer to our paper. While in real-world recommendation scenarios, there are actually not only just the user item interactions, there are actually exists lots of other information about users, such as the social relations. This kind of side information actually are very helpful for recommendation tasks, especially in the scenario for the sparse and co-stars users or items. So here in next part, I will introduce some representative papers focusing on how to incorporate the social relations into the solutions for recommendation tasks. So in addition to the user item interactions, the social relations among users provide another stream of potential information for understanding users' preferences. It's based on the idea that a user can acquire and disseminate information with their social neighbors, like classmates, friends, or colleagues, and so on. To put it another way, users' preferences are similar to or influenced by the people around them. And we call this type of methods social recommendations. Here is an example. You can see that some users prefers to watch the drama movie and others like the action films. It suggests that users in the same group are more likely to share similar preferences. On the other hand, data in social recommendations can also be represented as graph data with the user item graph and the user social graph. Moreover, here the user bridge the user item graph and the user social graph. For this category, we are going to introduce graph red model, which was proposed in IJCAI'2021. This work is one of the most representative GNN-based recommendations. Basically, the graph red model consists of three main components: the user modeling, item modeling, and the rating prediction. Here, the user modeling is used to learn the user representations, and the item modeling is used to learn the representations about items. In particular, user modeling utilizes two different aggregations to representatively process these two different graphs. One is the item aggregation. It used to understand users based on the interaction with different items in the user item graph. And the other aggregation is the social aggregation for learning the social relations between users in the social graph, which can help model users from the social perspective. Let's take a look at the social aggregation. In the social graph, the strong and weak times between users are mixed together. In this case, users are more likely to share similar tastes with strong ties than with weak ties. So the graph red model introduced the attention network to model the strength of user ties with networks. The attention rate, beta here, can be seen as the range of ties between users. Here, the social aggregation can be formulated in this equation, which aims to aggregate the item space user representation from the user direct neighbors. Here the MI means the user I's social neighbors. And the output HIS is the social space user representation of user I. Let's move on and take a look at these demos about social aggregation. In this slide, there are two graphs. The user item graph denoting the interactions between users and items, and the user social graph denoting the connections between users. Rectangled here that indicates the features information of a node. So we first use the item aggregation to learn the item space user latent factors in the user item graph with this blue circle. Then the social aggregation is proposed to learn the social space user latent factors from the social graph, as shown in this red circle. This red rectangle is the social space user representation. And that's is such from the social relations. Another important source we can use to benefit the recommendation task is the knowledge graph about items. So in next part, we will introduce the knowledge graph based recommendations. A knowledge graph actually is a heterogeneous graph in which a node corresponding to entities, and age is the relations. In recommendation scenarios, an item may corresponding to an entity in the knowledge graph, and then the knowledge graph provides these connectivities information between items via the different types of relations, and allow them to capture the semantic relations of the items. These connections can be found as triples with the head, relation, and the tail. For example, the triples, the forward gamut, and the film, and the rubric states the first step. The rubric is the director of the film's forward gamut. So the knowledge graph can provide an attractive source of relational information about items and can be harnessed to improve recommendations. So the question is coming: how to capture both high order structures and semantic informations in the knowledge graph. In this slide, we introduce a solution, knowledge graph convolutional networks, and end-to-end frameworks that can effectively capture the inner item relations by mining their associations attributes on the knowledge graph. This work was published in IJCAI'2021. The KGCN aims to automatically capture the both structure and the semantic information in the knowledge graph for recommendations. To model the relational heterogeneous knowledge graph, they propose to use the trainable and personalized relations function, score function, the pi u and r here, to transfer the knowledge graph into a user-specific weighted graph, which can have characterize the importance of relation R to the user U. Then to characterize the topological proximity structure of the item U, they compute the linear combination of the item V's neighbors. This step can be treated as the neighbors aggregator. Finally, we may further aggregate the entity's representation V itself and its neighborhood representation into a single vector and do the predictions with the user representations. Another method is the knowledge graph enhanced graph neural network based recommendation methods, the KGAT, which was accepted in KDB 2019. So here, the KGAT incorporates the knowledge graph here into the recommendation task. They consider the user node here as one type of entities, and the interactions between users and items as one of types of relations in the knowledge graph. So in other words, the KGAT incorporates these two graphs, the user item graph and the knowledge graph, into one large graph. They turn it as the collaborative knowledge graph. In such scenario, they can form a high-order relationship between users and items, and users and item, and the items and item, and the users and users, so as to explicitly model the high-order relations in the collaborative knowledge graph and provide a better recommendation with item size information. And as shown in this figure, the KGAT consists of three main components: the embedding layer, the attractive embedding propagation layer, and the prediction layer. In the embedding layer, the KGAT use various classes knowledge graph embedding methods to enhance the relations between the users and items and the relations. So it can help learn the each entities and the relations by optimizing this translation principle. Next, in the propagation layer, the KGAT use a knowledge-aware attention mechanism to perform the information propagation from its neighbors, and then update the node representation by aggregation function. Here, we shall pay attention to the knowledge graph aware attention, in which the the attention score depends on the distance between the head entities, EH, and the tailed entities in the relation R space to propagate more information for closer entities. And last, they just do the concatenation from all layers and generate the final node embedding and do the prediction. Now we have introduced two categories with size information enhanced, like using the social relations to enhance the user representation learning, and using the item in external knowledge to enhance the item representation and learning. So can we unify these two categories as one and have a more powerful recommendation methods? The answer is yes. Here we will introduce a method, GraphRex Plus, which was proposed in TKD 2020. In this work, we further consider the substitutable and complementary items to enhance the items representation and learning in social recommendations. For example, on some e-commerce platforms like Amazon or Taobao, they announce users to navigate between products through a link, such as user who bought item A also bought item B, or users who viewed item A also viewed item B. This paper is turned the GraphRex model in social recommendations by incorporating the source item graph to enhance the item representation learning. Item modeling part is quite close to the user modeling, where they have two aggregations, like the user aggregation on the user item interaction graph and the item to item aggregation. Okay, that is all for graph neural network based recommendation methods. In this slide, we just want to give some future directions. And although we can see the powerful GNN-based recommendation methods, we also find some limitation. The first challenge is that do we need deeper GNNs for recommender systems? And we can find that these more existing GNN-based recommendations can achieve better performance in a few layers because of the over smoothness issues. So we still need to understand why deep GNN model can benefit the performance of the recommender systems. And second, recently we find that deep recommender systems are also vulnerable to adversarial attack, and they can modify the training data to achieve their malicious goals. And so it's necessary to build a robust recommender system against this kind of adversarial attack. And we also in this slide, we also introduce our GAT model, how to build robust and reliable recommender systems. And okay, this is all for the GNN-based recommendation methods. Thank you. Next part, Xiangyu will present automatic machine learning technique for recommendation.